Hello, guys. Today we are going to speak about a different case. Okay, this I will consider as the third case. I don't know if you remembered, but we are speaking about how to find the roots, how to find the solution for high order, constant, constant coefficient, linear, and homogeneous differential equation. So today we are going to find how if we have imaginary roots, okay? How if we have imaginary roots, how to spot the general solution of this equation, okay? So as we are doing, okay, as we did also in the first or in the last video, okay, we just finished with everything about how can I say real roots, okay? When the imaginary when we have a homogeneous high order and high order and coefficient, constant coefficient differential equation. We did everything, and we ended up with such a formulas like, okay, the solution like CF is equal to Euler raised to M1 x times C1 plus Euler raised to M2 x times C2 plus infinite sum plus Euler raised to M n times x times Cn. Okay, we ended with this kind of formulas, okay, this kind of general solution, and this is the solution when we have like real roots and different to each other, okay. Here M is your root, first root, second root, and here it's enantiomer root, like n root, okay. That's the point. Now, then we ended with a general solution, general root, when we have like real, okay, real roots that are the same, okay, real roots repeated at all. So when we have real root repeated, so the general solution of this of the homogeneous differential equation should be something like Euler raised to M x times C1 plus x C2 plus infinite sum plus plus what? Plus x raised to n minus 1 times Cn. Okay? Now, we are going to now demonstrate, okay, from taking this equation as a base, we are going to show how to find, okay, how if the roots m here for this equation, how if these roots are not real, okay, how if we have imaginary roots in this. So please stay there. We are going to just do some good maths in here. So the first thing I'd like to say is that the same way we did for homogeneous when we had real roots, it is the same we are going to do, okay? The very same thing. So what do we have to do here first? See, the first thing we are going to do is to apply the substitution. So let's put, okay, I will put here, okay, put y is equal to Euler raised to v x. As I told you before, so v is a constant and x is the, how can I say, independent variable. Considering that y is a function, okay, y is a function of x, okay. Now, if we just write down this here, so we are going to have y, let me write here, so y is equal to Euler vx. Then we have to find what is y dash, what is y double dash. So y dash, y double dash. Y dash, what will it be? It will be v Euler raised to vx. Y double dash, v square Euler vx. Okay? So I will substitute this expression in this main equation. So what will it be then? So if I substitute all this one in here, I will get y, okay? Instead of y double dash, I will write v square Euler vx. In the place of this y, I will put this one, y dash. What is y dash? V Euler vx. And in place of of y, I will write the expression for y. It is Euler Vx equal to 0. Okay, now here we just have to put common our factor here. The common factor here is Euler raised to Vx. So Euler raised to Vx, and here V squared plus V and plus 2 is equal to 0. Okay, now we will do the same. So we will just have to forget. So see, what will be the solution for this equation? The solution for this equation, as I always said, okay, this one must be equal to 0, this one must be equal to 0, okay, so that this condition can be satisfied. But the point here is that it is not possible to this equation. There is no value for Euler or for x that can make this one equal to 0. No value for it, okay? So we will have just to find what is V here, okay? The value of V here that will make it equal to 0, the roots of V, we will substitute in here, and this substitution here, when we substitute the value of V that make it 0, in this expression, this expression that is substituted in V will be the solution for this equation, okay? Now, okay, let us solve this one. Here, we will end with this one, plus V and plus V squared, V equal to 0. So now this equation, as we can see, this one cannot be reduced to a, how can I say? This one cannot have a real root. Why? Because there is no number that if you sum will be equal to 1, and if you sum it will be equal to 1, and if you multiply will be equal to 2. Which number is this? There is no real number that can satisfy this condition. So in this case, what do we have to do? We have to find our solution for this one, okay? We have to find what? Applying this Bhaskara formula. You know how to find Bhaskara formula? Okay, maybe one day or in another video I will just play with this Bhaskara formula. But it's very easy. See, suppose you have ax squared plus bx plus c equal to 0. Okay, then what you have to do here, so you have to transform this one in a square, okay, roots in a, how can I say, perfect square, like a plus b square, that is equal to a square plus b square plus 2ab. You have to transform this and this. This is what Bhaskara did. So what you have to do first, to transform this one, what you have to do, the first thing is here, pick up this expression must be square. This is your a. The whole expression here will be your a. So for this one to be your a, it must be square, then b must be square, and so on. To accomplish this, I will just multiply here for 4a. Then if you multiply here 4a, everything, okay, and here 4a, so what you're going to have, we know that a here is different than 0. So multiply by this will be 4a squared x squared plus 4abx plus 4ac equal to 0. Now this expression now, this one, okay, you will consider as your a. This one. And then it will be 2ax squared plus, here also you have 2ax, that will be 2ab. So you're just to find what is your b. So 4ab, so it will be, if you just take this out, 2, it will be 2ax, and here I will get b. I don't know if you can see. So I'm just transforming this expression in a kind of perfect square. So this is 2ab and this is 1. This will be 4ac equal to 0. Now see, here you have your a, here you have your a. So this is your b. What does it mean? It means that to make it a perfect square, I have to add b square here, okay? B is b, yeah, it's just coincidence, yeah. For our b, I will consider as b, so b here, okay? So it means that to this one, to be perfect square, I have to add b square and take out b square, okay? So you are going to add here, plus b squared minus b squared. Then here, plus 4ac equal to 0. Okay? This b squared, this b squared. Only this expression right here, if you see well, this expression right here is a perfect square. And this expression is not a perfect square. So this expression can be written as 2ax plus b, okay, raised to 2, okay, square, minus b squared plus 4ac equal to 0. Now here, just send this guy out there. So 2ax plus b square will be equal to b square, okay, minus 4ac. Okay, this is your determinant, if you can see this well. Okay, that's why if determinant is different than less than 0, we can say that this is there is no roots for this one in domain of real. So this expression here, what you have to do, it is 2ax plus b equal to, this one can go there, this will be plus or minus root of b squared minus 4ac. Now send this guy there and this 2a down. You are going to have x1 and 2, because it will be two solution, will be minus b, okay, plus or minus root of b squared minus 4ac all upon 2a. Okay, yeah, that's how we do for this one. So for this one, okay, this is the general solution. So here we have a square, so we will just apply this formula directly. Okay, let's go for what is really interesting. I just played this because, yeah, I saw that's necessary. This is Bhaskara. So let's go for what is really important. Now see, here we have to find first what is our delta. We know what's delta. Delta is the inner part. When we have x 1 by 2, 1 and 2, this will be minus b plus or minus root of delta upon 2a. Delta is b squared, as I did, b squared minus 4ac. Okay, so delta is a square. So here what is a? A is 1, b is 1, c is 2. So b squared minus 4ac. What will it be? It will be b. B is 1 square minus 4. What is a? A is 1. And what is c? C is 2. If you just multiply all of them, you are going to have what? 1 minus 8. It will be minus 7. Okay? 1 minus 8, it will be minus 7. So minus 7. In real, in domain of real, there is no root for this one. But that's why we are talking about imaginary roots, infinite imaginary roots. Okay? As here, I will get v will be v1 and 2 will be equal to, okay, will be equal to what? Will be equal to minus b. What is b? B is 1, so minus 1 plus root, okay, plus or minus, let me write here, plus or minus root of delta. What is delta? Delta is nothing more than your minus 7, because we calculated here. Delta is b squared minus 4ac, and delta is 1 squared minus 4, 1, and 2. This gives you minus 7. So it gives you minus 7. Put there minus 7. Okay, then it is by 2a. Okay, 2a is 1. So yeah, it will be only this expression. Now, we will have to add a bit of concept, like a concept of imaginary number. We know that whenever we have minus 1, root of minus 1, it is I, okay? Because I square is equal to minus 1. Okay, this is what we are going to do here. So if we change here, you're going to have 1, okay, v1 and 2. It will be equal to minus 1 plus or minus. Here, I'll get 7i squared, all by 2. And this will be equal to what? Minus 1 plus, here, plus or minus. Okay, this root will be out. So root of 7i, all by 2. Okay? Now, in this expression here, we have two solutions. So it means that the solution here is like v1 is equal to minus 1 by 2 plus root of 7i. Okay? All by 2. Then the other one, v2 is equal to minus 1 by 2 minus root 7 by 2i. Root 7 by 2i. Okay? This is the solution. Now see, here we have a complex number where this first expression is our real expression. Minus 1 by 2 is a real expression, and this one is the imaginary expression, okay? The real term and the imaginary term. So now from here, what you're going to do, we will do the same thing we did, okay? Okay, we will do the same thing we did. So we have to substitute this value that we have found in this expression. So the first solution will be, okay, the first solution will be something like this. Yeah, something like this. Euler raised to V1 x, okay? So how can I change this one? This is the first solution, and this will be the second solution. Euler V2 x, just in this way, okay? So here, what you're going to see, this expression, I will just first do for this one. V1 is what? Euler raised to minus 1 by 2 plus root 7 by 2, okay, time I, all multiplied by x, okay? That's the equation, that's the point. This is for the first root. Now see, this is for the first root. So, okay, this is for the first root. Then we have to also add the second expression. Okay, I will just do this one directly, plus or minus. Okay, instead of separating this, of separating them, I will just write it, but I can separate, no problem. Okay, I will just separate, no problem. So this one is as it is. So this one is equal to this, right? So what does it mean? It means that I can write this in this way. This will be equal to minus by 2, okay? Euler raised to minus 1 by 2 time Euler raised to root 7 by 2 I. And we know that this x is multiplying, okay? So it will be multiplied by x, okay? And here also multiplied by x, okay? Okay, this will be minus 1 by 2 multiplied by x. Now see what you have here and see what you have here, okay? What you have here is Euler raised to minus 1 by x, 1 by 2x. And then you have a imaginary number here. This one is multiplied by this, okay? So now how do we write this expression, okay? That's the point. How do we write this expression? This one will remain as it is, but this expression have to change somehow, okay? How to change this expression then? Let us see how will it work. So you, I guess you don't know, but I'm lack of space. I need space here. See, Euler, we know the equation of Euler. Euler's equation, when we have I theta, Euler raised to I theta, it's equal to cos of, okay, cos theta plus I sinus theta. Okay, this is Euler's equation, and this is what we are going to apply here for this one. So here we have in the second, remember, like we have Euler raised to root 7 by 2 I times x. So what does it mean? It means that it will be equal to what? Okay, what is theta, what is I here? So theta will be all the expression that is not containing I. So this one and this one is your theta. So you can just write here like this, root 7 by 2x and I here, okay? So it will be equal to cos root 7 by 2, sorry, root 7 by 2x, okay, plus I sinus of root 7 by 2x. Okay, that's the expression. As you can see, okay, this will be the expression for this equation. Okay, now see, no matter, this is only for one equation. Okay, if we draw or if we do, the second expression will be the same. Okay, if we do for, suppose, let us see, suppose for Euler raised to V2 x. This will be Euler raised to minus 1 by 2, then minus root 7 by 2 I times x. It will be Euler raised to minus 1 by 2 x times Euler raised to minus, here I will get minus, then minus root 7 by 2 I multiplied by x. Okay, so if you do the same for this point here, for the other point, what will you get? Okay, just draw for this one. So when it is negative, just put for this negative here, this point here for this negative. I will get something like this, Euler raised to minus root 7 by 2 I, okay, x, and that will be equal to cos of root 7 negative by 2 x, okay, x. So then what we are going to have, yes, minus, okay, minus, then here we are going to see something like plus I, and again, as you can see here, okay, I, then sinus of root 7 by 2x, okay, by 2x. So what we now end with, that's the point. So as they are, okay, they are very same expressions, like they are a pair conjugated. This is minus, okay, this is for this minus. So what you are going to have here, this is plus, okay, yes, this is plus. Now from here you can just directly see that this equation will be the same also, okay, yeah, this will be the same. Yeah, okay, just as we were talking to you guys, so here we will get this expression here, okay, this expression here. So for the second expression, it will be this and this and this. Nice. Now the question comes, okay, this is for the second expression here, and this is for the first one, okay, for the first one. This is the first thing, the first solution, and this is for the second solution. So we know how to write now the first solution and second solution. How? See, the first solution, okay, will be written as y1 will be equal to Euler raised to minus 1 by 2, okay, x time. Here, in place of this expression, I will write this Euler equation. This will be cos of root 7 by 2x plus I sinus root 7 by 2x, okay, root 7 by 2x. And the second expression will be the same as we told you guys. This for the second expression, y2 will be Euler raised to 1 by 2x, and here cos, we know that cos is a even function, so cos of minus this one will be the same of this. But sinus is a odd function. It's an odd function. So if it is an odd function, so sinus of minus root 7 by 2x, it will be minus I sinus of this expression. So this will be the same, root 7 by 2x, and here minus I sinus root 7 by 2x. Okay? Yeah. That's the point. Now see, this is first solution. I will multiply by C1, and this is the second, C2. Okay? Now I will write it all together. Okay? I will write it all together. Okay? I can write like C1, C2, or I can just write like Q1 and Q2. It's up on you. See, if I put all this together, what will be my CF? That's the point. Can I erase? I will just erase this part over here, because I ain't got no place, no more space. I got no more space. Okay. I will write all the CF. What will be my CF here? CF will be Euler raised to minus 1 by 2x multiplied by cos root 7 by 2x plus I, okay, I sinus root 7 by 2x. Then plus Euler raised to minus 1 by 2x multiplied by cos of root 7 by 2x minus I sinus of root 7 by 2x. Okay, this will be the solution. So I can take out this one common. So Euler raised to minus 1 by 2x. So it will be what? Ah, sorry, I forgot. Here it is multiplied by Q2, and here is Q1. Okay, do not forget about this. It's Q2, Q1. Okay, take this one and take this one common. They are common. So this is common. So it will be this time this. This will be cos root 7x, 7 by 2, okay, time Q1 plus I sinus root 7 by 2 x Q1. And here I got plus cos root 7 by 2 x Q2 minus I sinus root 7 by 2x Q2. Okay, just put together sinus and sinus and cosinus and cosinus. Okay, put all together. What you'll get? Euler raised to minus 1 by 2x cosinus Q1 cosinus Q2. It will be Q1 plus Q2 cos of root 7 by 2x. Okay, plus now here sinus we have Q1 I, okay, we can just put here out I and here put Q1 minus Q2 sinus, okay, sinus root 7 by 2x. Okay, now what you have to do here, see, there's one Q1 plus Q2 and Q1 minus Q2. I can call this one directly Euler raised to minus 1 by 2x. Here it is, I will call C1. Okay, C1. These are all constant, C1 plus I, this I will call C2 sinus root 7 by 2 because they are all constant. Now see, that's the expression, that's the solution, okay? So when we have imaginary different imaginary equations, okay, this will be our expression for when we have like a second order higher degree, when we have higher degree and it is second order, so we will end only into solutions. And these two are the solutions, right? Now, what will be the general way to write down this expression, okay? The general way to write down the solution when we have imaginary number. So the first thing you have to understand is that imaginary number are always presented themselves in pair, okay? They are all in pair, okay? Like in this way, so they will present themselves in pair. What we mean by pair? I mean that imaginary number, they are all like this. So Z is equal to alpha. This alpha is the real part of this imaginary number. And plus or minus beta, like beta. This is beta, beta I, okay? Imaginary numbers as a solution, they are always represented in pair, okay? Always represented in pair. That's why when we have an imaginary number like this, okay, when we have infinite imaginary roots, they will be infinite imaginary roots, but they will present themselves in pair, as you can see here, okay? We got a pair of imaginary roots, okay? So how to write infinite imaginary roots infinite pair of imaginary roots. Okay? Suppose I have, well, CF will be equal to Euler. See, look here. This is your alpha, because what you got was something like this. V was equal to minus 1 by 2 plus, okay, plus or minus root 7 by 2. Then here you got your I. Okay? So this one is your alpha, and this one is your beta. Okay? Beta I. Okay? So this is what you're going to do. Okay? This is what you're going to do. See, this part is your imaginary number. So if you see what is your, sorry, not imaginary number, your real number. If you see here, you put the real part of the solution, of the imaginary number you got. The real part will be here, okay? Time here, just by checking. So this will be alpha time x, okay? Multiplied by C1, okay? C1 time cos. What is this? This is beta. This is your beta. Beta x plus I. This is for one pair. When I have one pair of imaginary number, this is the solution for one pair. Now if we have infinite pair, we have just to repeat again and again and again. So C1 cos beta x plus I, okay, I sinus beta time x multiplied by C2. Okay, multiplied by C2. This is for one pair. Now Veloso, suppose we have more than one pair. Suppose we have, let's see, suppose we have V is equal to, suppose alpha plus or minus beta I, and V, this is for the first pair. The second pair, 1 and 2, and this is 3 and 4. We have a different pair, okay? Suppose we have a different pair, okay? Like this one. This one is a pair of different roots, okay? Just like this. Suppose it is like a different pair. We have a different pair. So V1, V2 is this. V3, V4 is another one that is different one. Let me call this one theta, okay? Plus or minus. And here I few, then I few. So what should it be? That's the point. So suppose we have 4, okay, 4 roots, but they are 2 pair of imaginary numbers. So then you have just to add the second pair upon the Euler raised to theta time x, okay? This will be plus Euler raised to theta x, then C3 cos phi x plus I sinus phi x times C4. Okay? Then suppose you have more and more and more infinite, so you have just to write like this, in this way. Okay? And that is how we demonstrate to infinite imaginary roots that are different. Okay? Okay, infinite. Let me write just one. They are different. Okay? It is for different imaginary roots. Okay? Just for different imaginary roots. We have two, like when we have one pair of different imaginary roots. Okay? Suppose we have 2 pair. Here we have 2 pair, and these 2 pair are different pair of imaginary roots. Okay? Now suppose we have this pair is equal to this one. How to write? Suppose we have V1. The first pair, 1, 2, is equal to the second pair. Like this pair is equal to this one. Is equal to the second pair, 3, 4, root 3, 4. And it is equal to alpha plus or minus beta I. How to write this kind of things? How to write this solution? Okay? To write this solution, you have to just apply this old method that we have done. Okay, and this will be in the next lecture represented. Okay, now just want to tell you guys, please do not be afraid to share your video, share your comments, share your feelings about everything. So yeah, please subscribe, put your notification, so and things will be good for us. This is a suggestion for a good friend of mine, a Chelson, so a very good engineer, and yeah, a genius mind. Yeah. Thank you, Mushesha. Bye.